Spudis to give an overview for the Human Exploration and Destination Drivers session, and the talk is entitled The Moon as an Enabling Asset for Spaceflight. Paul.
Thank you. Thank you very much. I want to talk about this problem of the strategic direction of our space program from a slightly different perspective. How do I advance this? Okay. First of all, let's outline what the problem is. We've been sending people into space for 50 years, and we haven't really changed the template of that. We build custom-built spacecraft, we launch them, we discard them in flight, and then we come back, usually with a very small piece of the spacecraft. What's more, we drag up with us everything we need in space on every single mission. And there's something I like to call dumb mass. Dumb mass is mass that has to be launched from Earth, but has very low information density. An example is propellant or life support consumables. So that problem basically limits us in the amount of things we can do in space because we're mass and power limited, we're capability limited. So let's think instead about an alternative model where we basically acquire the dumb mass that we need to support human life and to conduct exploration, but get that material not from Earth but from space. If we could do that, if we could find a way to break that problem, it would enable a wide variety of different experiences in space. So what is really our objective? A lot of times you'll hear, and this was in fact in the recent NRC report that was alluded to earlier, that Mars is the ultimate goal. NASA's fond of saying this too. I respectfully disagree with that. Mars is a goal. It is not the goal. It is one goal among many other goals. I would contend that our real desire for spaceflight is to be able to go wherever we want, whenever we want, for whatever purpose we can imagine. Now that's a very tall order. Right now we're light years from such a capability. We want freedom of motion throughout space to do all kinds of different jobs, not just science and not just exploration, but things like utilization and construction. All these things that are desirable is what we're after. So we should think about systems that point in that direction, not systems that repeat what we've always done, but systems that do something new and different. We want to become basically mass and power unlimited in space, not capability limited. I think the analogy here is to seafaring rather than aviation. Traditionally, space has always been compared to aviation, but in fact, you really want a navy. You want a space navy that's able to sail to the different ports and the different locations in space. So what's the problem? If this is so desirable, why is this so difficult to achieve? Well, there's a lot of reasons, and the biggest reason is something my friend Don Pettit calls the tyranny of the rocket equation. Now, the rocket equation was first outlined by Tsiolkovsky at the beginning of the last century, and he showed that for a given amount of propellant, you could only send a very small amount of material into Earth orbit. And of course, once you're in Earth orbit, if you want to go somewhere else, you have to apply another impulsive maneuver, which means you have to carry the fuel for that with you. And effectively, as those things add up, you come to a very small and diminishing fraction of useful payload compared to the mass of the rocket. The best rockets we have now have a mass fraction on the order of about 0.85 to 0.9. That means 85 to 90% of it is propellant. Spaceflight is expensive because of that. It's expensive because you have to drag up all this stuff with you into orbit. And it's also interesting to think about the following. It's barely possible. If the mass of the Earth was 50% greater than it is now, then the chemical energy in the typical chemical propellants we use in rockets would not be enough to impart the momentum we would need to get into orbit. So we could barely get into orbit. It's very expensive to do so. It's expensive to remain there. And in fact, the benefits of all that are not intuitively obvious. They have to be explained to people. If they were intuitively obvious, we wouldn't be having this conversation. So let me put it another way. If our ultimate goal is to go anywhere and everywhere, and if we're always going to be capability limited because of the mass and power limitations of the rocket equation, we need to find a different template, a different way of doing things. And I contend that to create new capability, we need to learn to use what we find in space to create that new capability. And that's my theme. That's why I call the moon as an enabling asset. So just to recapitulate here what I'm talking about, our current template is to custom design spacecraft, put them on an expendable rocket, conduct the mission, acquire whatever information that we want to from that mission, and then throw it away. And then we go back to square one. We start from scratch again. But suppose instead you built a system that consisted of small pieces that were able to operate as a complete integrated system. So in other words, you're actually building an infrastructure, a permanent spacefaring infrastructure in space that you can actually reuse again and use again and again. And effectively, what allows you to do that is the ability to take what you find in space and convert it into a useful form. So effectively, you're building a system that can be expanded indefinitely and effectively increases human reach incrementally. Now, we think a lot about our business. We think about science. We think about exploration missions, about going to distant places and exploring. But in actual fact, space is much broader than that. Space is intimately woven into the fabric of modern technical civilization. We depend on it for almost everything: communications, global positioning systems, national security, in addition to science. And most all of these satellite assets that permit this are in the volume of space between Earth and the Moon. There are a lot of assets in low Earth orbit, but a lot of the really useful space application satellites are in cislunar space. They're in orbits above LEO that it requires additional energy to get to. And in fact, we can't access those satellites, at least not readily, not with people and not with robots. We basically build single function spacecraft, use them for a while, and then abandon them, and then launch new spacecraft of a better generation. Now, the interesting thing is that we've learned from the past 30 years of the shuttle station program that there's another way of doing things. Effectively, people and machines working together in space can actually assemble large distributed systems that have much more power and much more capability than anything we could launch on even the biggest rocket that exists now or in the future. Effectively, think about the International Space Station. It's a 100-ton spacecraft, 100 kilowatts of power generation. It was assembled by people and robots over a period of 10 years. And it's the biggest thing we have in space now. Imagine a satellite like that in geosynchronous orbit as a communications satellite. In one fell swoop, on one hemisphere, you would effectively replace and make obsolete the entire terrestrial cell phone network. You would have 5,000 channels of high-definition television on your iPhone. And effectively, there would be no blacked out areas anywhere within that hemisphere. Such a thing is possible if you were able to get the pieces and people and the machines to that distant orbit to assemble a spacecraft like that. So what I'm contending here is that that capability requires us to build a system that is permanent and reusable and extensible. And the moon allows us to do that. So how does that work? Why is the moon important in all this? This is a slide I show in a lot of the talks I give about the moon. I kind of summarize the value of the moon in three pieces. It's close, it's interesting, and it's useful. Now I'm going to concentrate today on the number 1 and number 3 because I'm interested in the utility of the moon, the ability of the moon to be an asset to spaceflight. The closeness is actually quite significant. It allows us to do things at a much more inexpensive and flexible way than it would if we were trying to harvest the resources of an asteroid or even a distant planet. The usefulness, in fact, depends on what we found out about the moon within the last 5 years. So let's talk about the proximity first. The moon is in Earth orbit, and what that means is you can go to the moon at any time. There is literally always a launch window available to go to the moon. You hear about the Apollo launch windows. All that was because of the fact that they had to land at a certain time of the lunar day, and they needed to have certain illumination conditions. Once you're on the moon, though, there's no requirement to land at the beginning of at lunar sunrise. You can land any time during the lunar day. You can always get to the moon. There's always a launch window open. The delta V to the lunar surface is quite low. It's about 6 kilometers per second from low Earth orbit. In comparison, the Martian surface is about 10 kilometers per second. And what's more, it's very close in terms of time. You can, and if you go on a Hohmann-type trajectory from Earth orbit to the moon, it's anywhere from 3 to 5 days. Very large cargo-like vehicles can take slow boat routes using, for example, solar electric propulsion and weak stability boundaries. They can get there in a matter of weeks to months. You don't really care because it's all cargo. So in actual fact, it's very accessible, both in terms of time and energy. One thing that's really important about human missions is that you're always able to develop a reasonable abort scenario. And if you don't think that's important, ask the guys in this picture who, in fact, were on their way to the moon when their service module exploded, and they got back by the skin of their teeth. And in fact, that is actually an important consideration that's not been thought about in great detail. People have thought about it and worried about it, but the tendency is to say, well, we're going to take those risks and do that. I contend that in the exploration game, you want to learn to crawl before you try to walk. And finally, the point I want to make is that the round-trip light time between Earth and Moon is 3 seconds. And what that means is you can control robots in near real time with operators on the Earth. What that means is that it allows you to send quite capable and sophisticated machines that are operated by operators on the Earth that can do quite a bit of work on the Moon. And in fact, to my mind, this is the key to making lunar return affordable. You basically try to do most of the stuff you want to do with robots before you send people. So the other value of the Moon is the utility of the Moon. And this is some of the things we found in the recent years, primarily material and energy resources. The most important material you can get from any object in space is water, because it's extremely useful. Think about it. It's a form of life support. You can drink it, use it to reconstitute your food, sanitary purposes. You can also crack it into its component, hydrogen and oxygen, and breathe the oxygen. You can use water as a medium of energy storage. In fact, if you a rechargeable fuel cell will break apart water when it's illuminated by the sun to make hydrogen and oxygen. You can recombine those gases in the fuel cell when you're in eclipse to generate electricity. It's a completely reversible process. Water can jacket your habitat. It's the best shielding material we know of to protect you from hard cosmic radiation. But the most important use of water is its use as rocket propellant. Liquid hydrogen and liquid oxygen are the most powerful chemical propellants that we know of. And in fact, the Moon, we now know, contains hundreds of millions of tons of water in areas around the poles. And in fact, it's what Tony was talking about, the Prospector mission is a good start on helping us to characterize exactly what form that water is, where it is, and how we can access it. But in addition to the material of the Moon, we also have the energy resources of the near permanently lit areas. Now, there's no area at the pole that's lit all the time, but there are areas at the poles that are lit for more than 90% of the lunar year. So in fact, there are extended periods of illumination in some of these high areas that would allow us to effectively maintain near permanent presence on the lunar surface. The small times when we're in eclipse, we can bridge those with rechargeable fuel cells. But in addition to the material and energy resources, you have the lunar environment, which is unique and useful for a lot of scientific experiments and a lot of industrial processing. And finally, the Moon is a real planet with real geology where you can actually learn how to explore a planet. Now, we did a great job with Apollo. When the crews landed, they had a few days to explore. They had to go everywhere and do everything they could in the shortest amount of time. That's not the most optimum way to do geologic exploration. What is appropriate for people to do on the Moon? What is appropriate for robots to do? And more importantly, what is the best mix of those two methods to get the most exploration value for the dollar? That's something we can actually learn by working on the Moon. So, if I can kind of summarize where I'm going with this, what I want to imagine is a system that basically extends human reach beyond low Earth orbit in an incremental and accumulative manner with small pieces. You want them small so that it's affordable. You can effectively make something as cheap as possible by sending it in very small pieces. And yet the pieces have to act together and work together cumulatively as a big system of systems. You can do this on the Moon because the Moon is close, and so you can initially land with robots, do a lot of the construction work, a lot of the preparation work, and effectively assemble a lunar outpost by robotic control from the Earth so that humans that arrive at a turnkey facility. And in effect, you schedule, in this case, would be a free variable. We don't really care how long this takes because we know where we're going and we know what we're trying to do. Just a brief slide. This refers to a paper that Tony Lavoie and I published 2 years ago. I call it an affordable lunar architecture, not the affordable architecture. This is one of many. But any architecture has to have these basic principles of robotics first, establish infrastructure and capability on the surface, followed by people later. All of these things can be scaled so they can be affordable under a variety of different budgetary regimes. So, what will we have from this? If we actually build a system like this, and in the case of the architecture we described, we leave our pieces in space. It's a space-based architecture. We refuel elements such as the cislunar stage and the Earth return stage and the lunar lander from lunar propellant made from lunar water at the poles of the Moon. So in effect, it is a permanent spacefaring system supplied by the resources of the Moon. You're building what is in effect a transcontinental railroad in space. And as the Transcontinental Railroad not only opened up the west coast of the United States, it also opened up the interior as well. You were able to transport people and cargo to every point in between. And remember, the points in between Earth and Moon is the pay zone. That's where all of our satellite assets currently reside. So the Moon is an enabling asset in the following sense. It's a testing ground and a proving ground for the skills that we need to become a spacefaring exploratory people. But more importantly, it's a logistics depot. It allows us to get the dumb mass, the consumables, the propellant, the things that we need to build big structures in space from the materials of the Moon. And these are skills that you have to master if humanity is ever to have a future beyond a simple expedition where you launch from the Earth and you return in a small capsule. So what kind of space program do we want? Do we want a series of one-offs where we build a system, we launch it, we do a flag and footprint, and we come home, and then we cancel the program? Now, effectively, by adopting that architecture for Apollo, it had within it the seeds of its own demise. Once you accomplished the mission of landing on the Moon, there was no reason to go back. So effectively, we lost it because of that reason. Instead, I suggest that what we want to do is to build a system that incrementally increases the reach of humans, first from LEO, then into cislunar, and then beyond to the planets. And you can do that by using the Moon and its assets. And I'll leave you with that thought. Thank you very much.
Wonderful. Thanks so much, Paul. I would imagine there might be a question or two. Yes. If you could wait for the mic.
John Cooper, NASA Goddard. On the Transcontinental Railroad, that was really a system to develop the habitability of the western, United States. Exploration, of course, occurred many years before that. So the question is, are we doing exploration, or are we doing habitability here?
Yes. Because if you don't do the economic part with the exploration part has within it the seeds of its own termination.
Please.
I have a quick question regarding your very last statement, that how you see this, that government develops and tests technologies and commercial sector would follow. Maybe it would be even made more affordable if commercial technologies would be integrated from the beginning into this process in the same way as like COTS program and so on competitive basis, so leveraging the capabilities that commercial sector already has and can develop very soon.
Well, I don't mean to suggest that this is the only way you can go forward. There's a lot of architectural variables you can tweak. One of the advantages of a system that is incremental like this is that there are many on-ramps and off-ramps for both international partners and commercial partners. So it's much easier to integrate that aspect of the program into an architecture like this than it is into a fixed architecture like an Apollo-style mission.
Other questions? I actually have one for you, Paul. I'm wondering how much of a challenge you see building the much more reliable systems that would be necessary, that would last decades versus a handful of years.
Sure. I mean, there are challenges. I don't mean to suggest that this is going to be a piece of cake, but the advantage of small pieces is as they wear out, and if you really can't fix them to make them last longer, you can always launch the small piece of replacements from the Earth if you need to. We, in fact, have looked at this in some detail in regard to the lunar surface aspect of the architecture, and we've even looked at things like changing out the engines of the lunar landers so that we could continue to use them for anywhere from up to 50 flights. So it's a challenging thing to do, but this is what we need to learn how to do if we're going to become spacefaring.
Sure. And I can imagine 3D printing and whatnot would play into that. Well, right. Yeah. All right. Time for one last question, if there is one. Bill Baki.
Hi, Paul. Have you compared the economics of your system where we're extracting water from the poles of the moon versus getting water, let's say, from carbonaceous chondrite near Earth objects, and what the relative cost benefit is of both?
I haven't done that specifically, but in fact, one of the advantages of lunar water over asteroidal water is that lunar water is in a free state. That the water in near-Earth asteroids are all chemically bound in phyllosilicates, whereas the water on the moon is basically present as ice. So all you have to do is heat the icy regolith and you'll extract the water. There may be quite a few steps required to extract water from an asteroid. Also, gravity is very useful when you're processing material. Now you can form artificial gravity when you're working on asteroid processing by spinning the thing, but it adds a great deal of operational complexity to your system. The moon already has gravity. It's useful for things like convection that you might want to use in your processing stream.
Thanks, Paul. Okay.